Watch this rocket launch. That's an Atlas V, America's most reliable launch vehicle. It's carried Mars rovers, military satellites, and billion-dollar payloads into orbit. Now look closer. Look at the base. That engine, the one doing all the work, wasn't built in America. It was built in Russia, the RD-170, designed by engineers who spent the Cold War trying to beat us to the moon. And now we buy them, not because Russian engines are cheaper, not because of some trade deal. We buy them because America, the nation that built the Saturn V, the nation that landed on the moon, forgot how to build rocket engines this powerful. The F-1 engine generated 1.5 million pounds of thrust. It flew 65 times without a single failure. It was the most reliable large rocket engine ever built. Today, 3 of them sit in museums. We can't rebuild them. The RD-170 generates 1.77 million pounds of thrust. It's the most powerful liquid rocket engine ever fired, and it's still flying. Its descendants power American rockets right now as you watch this. Here's what should make you furious. We didn't lose this technology in a war. We didn't have it stolen. We just stopped. We let the engineers retire. We let the documents gather dust. We let the knowledge die. And when we needed powerful engines again, we had to call Moscow. This is the story of how America built the greatest rocket engine in history, then forgot how it worked, and how our Cold War enemy kept building while we dismantled everything. To understand what we lost, you need to understand what the F-1 actually was. It wasn't just a rocket engine. It was an engineering achievement that pushed the absolute limits of 1960s technology and human intuition. 1.5 million pounds of thrust per engine. 5 engines on the Saturn V first stage, generating 7.5 million pounds of combined thrust. Fuel consumption was 3 tons per second. That's a backyard swimming pool's worth of kerosene and liquid oxygen every 15 seconds, converted into controlled violence. But the numbers don't capture the real challenge. The problem that nearly killed the F-1 program was combustion instability. Inside the combustion chamber, at pressures exceeding 1,000 pounds per square inch, the burning propellant would oscillate at frequencies around 2,000 cycles per second. These oscillations would build on themselves, creating standing waves that could tear the engine apart in milliseconds. During early tests, combustion chambers literally exploded on the test stand. Rocketdyne engineers spent years solving this problem, over 2,000 test firings. They tried different injector patterns, different chamber geometries, and different fuel mixture ratios. This wasn't elegant physics. This was brute force trial and error. They'd make a change, fire the engine, and see if it exploded. If it didn't explode, they'd try to understand why. Eventually, they developed solutions, baffles in the injector face, specific hole patterns that disrupted the formation of standing waves. But here's the critical detail. Much of this knowledge was never fully documented. Experienced technicians could diagnose combustion instability problems by sound alone. They could hear the frequency shifts and the harmonic patterns, and they'd know exactly what was wrong. No computer models, no simulation software, just intuition built over years of listening to engines scream. This was the black magic of rocket engineering. The F-1 worked not just because of good design, but because of accumulated human expertise that existed nowhere except in the minds of the people who built it. Now, consider the Soviet answer. The RD-170, 1.77 million pounds of thrust, the most powerful liquid-fueled rocket engine ever built, and it's still flying today. Valentin Glushko designed it. While America was celebrating the moon landings, Glushko was solving the same combustion instability problems we had faced, but with a different approach. Instead of one massive combustion chamber like the F-1, the RD-170 used 4 smaller chambers fed by a single turbo pump. Smaller chambers meant shorter acoustic wavelengths, which made instabilities easier to control. But the real innovation was the thermodynamic cycle. The F-1 used a gas generator cycle. A small portion of the propellant gets burned in a separate chamber to drive the turbopump, then exhausted overboard. It's simple and reliable, but inefficient. Only about 65% of the propellant energy converts to thrust. The RD-170 used staged combustion. All of the propellant flows through the turbopump. The fuel is burned oxygen-rich at extreme pressure to drive the turbine, then injected into the main combustion chamber where it burns again. Nearly 99% of the propellant energy converts to thrust. It's thermodynamically elegant. It's also viciously difficult to build. Staged combustion means the turbopump operates at pressures that would make the F-1 engineers weep. One seal failure, one crack in a weld, and superheated oxygen-rich gas finds its way where it shouldn't be. The result isn't a malfunction, it's a detonation. American engineers tried to develop staged combustion engines in the 1960s. They kept failing. The metallurgy wasn't good enough. The welding techniques weren't precise enough. The seals leaked. So we stayed with gas generator cycles. Reliable, proven, and less efficient. The Soviets kept working on it. Their metallurgy improved. Their welding techniques improved. By the 1980s, they had solved problems we had given up on. The irony is profound. We thought we were ahead. We were solving the wrong problem. The RD-170 first flew in 1985 on the Energia rocket, the Soviet Super Heavy launcher designed to compete with Saturn V. It was 20 years too late to win the moon race, but it proved something important. Soviet engineering hadn't just caught up. In some ways, it had surpassed us. But first, the F-1 had its moment of glory. July 16, 1969, 5 F-1 engines ignite beneath Apollo 11, 7.5 million pounds of thrust, lifting 6.2 million pounds of rocket. Neil Armstrong's heart rate at liftoff was 110 beats per minute. That's calm. For a man sitting on top of a controlled explosion, the engines performed flawlessly for 150 seconds, burning through 4.5 million pounds of propellant before shutting down and separating. The upper stages took over, and 3 days later, Armstrong stepped onto the moon. 65 consecutive flights, 0 engine failures. The F-1 wasn't just powerful, it was reliable in a way that no engine of that scale had ever been. It was the engineering triumph of the 20th century. 16 years later, the RD-170 had its own proving ground. February 1986, the first full-duration test firing at the Baikonur Cosmodrome. Engineers expected problems. New engines always have problems. The RD-170 ran flawlessly. The test was so uneventful that engineers later called it boring. In 1988, the Energia rocket, ET, launched the Buran spacecraft, the Soviet space shuttle. The RD-170 engines on the strap-on boosters performed perfectly. Buran completed an unmanned, fully automated orbital flight and landing. The Soviets had proven they could match Saturn V capability. It was 2 decades late, but they had done it. And then, both nations threw it all away. But only one of them recovered. Apollo ended in 1972. The last Saturn V launched Skylab in 1973. Production stopped, the assembly lines shut down. Rocketdyne engineers were reassigned, retired, and laid off. The institutional knowledge began to evaporate. The documentation was complete. Thousands of pages of blueprints, specifications, and test reports. NASA assumed this was enough. If we ever needed to build F-1 engines again, we had the plans. We could just start manufacturing. This assumption was catastrophically wrong. In 2013, NASA launched an effort to study the F-1 for potential use in the Space Launch System. Engineers brought out the old blueprints. They examined the museum artifacts. They interviewed the few surviving engineers who had worked on the original program. And they discovered something terrifying. The documentation was incomplete. Not in the sense that pages were missing, but in the sense that documentation can never capture tacit knowledge. The blueprints showed dimensions and materials, but not the reasoning behind the decisions. Weld techniques were referenced but not explained. Material specifications were ambiguous. Tolerances that felt right to 1960s machinists were impossible to replicate with modern techniques. One engineer summarized it perfectly. "We have the blueprints, but we don't have the understanding." The F-1 wasn't just a design. It was a living body of knowledge, carried in the hands and minds of the people who built it. Recipes don't make you a chef. Blueprints don't make you a rocket engineer. And by 2013, the people who knew were dead or in nursing homes. We had built the most reliable large rocket engine in history, and then we forgot how it worked. Meanwhile, in Russia, something different happened. The Soviet Union collapsed in 1991. The economy disintegrated. Funding for space programs evaporated. But NPO Energomash, the bureau that built the RD-170, kept the production line warm. Engineers stayed employed. They weren't well paid. They weren't working on glamorous new projects. But they were employed. The knowledge transferred to the next generation. Older engineers trained younger ones. The tacit knowledge, the intuition, the black magic, it all survived. The RD-170 evolved. The RD-171, an improved version. The RD-180, a two-chamber export variant. The RD-191, a single-chamber engine. Each iteration refined the design, but the core knowledge remained intact. By the late 1990s, Russian rocket engineers were broke and demoralized, working in crumbling facilities. But they were still building the most advanced rocket engines in the world, and then came the humiliation. In the 1990s, Lockheed Martin needed an engine for the Atlas III rocket. The American options were inadequate. Nothing was powerful enough. Developing a new engine would take over a decade and cost billions. So Lockheed looked elsewhere. In 1996, they signed a deal with NPO Energomash, the RD-180, 860,000 pounds of thrust, staged combustion cycle, Russian-built and American-financed. The first Atlas III launched with an RD-180 in May 2000. American rockets with Russian engines. The same engineers whose predecessors tried to beat us to the moon now powered our military satellites, our planetary missions, and our national security infrastructure. For years, this arrangement was quietly accepted. The RD-180 was reliable, cost-effective, and available. We'd become dependent on it. Then, in 2014, Russia invaded Crimea. Congress panicked. Suddenly, the fact that American space access depended on Russian engines became a national security crisis. There was a scramble to find alternatives and to restart domestic engine production. But it was too late to rebuild quickly. The knowledge gap was too wide. The industrial base had atrophied. We had beaten ourselves. Consider the alternate timeline. What if Saturn V production had continued? What if the institutional knowledge had been preserved? In the 1970s, NASA studied the F-1A, an upgraded version generating 1.8 million pounds of thrust. It was feasible. The technology was mature. It was canceled. What if we had pursued staged combustion in the 1970s instead of abandoning it? We could have developed an American equivalent to the RD-170 by 1985. That would have meant cheaper access to orbit, larger space stations, and Mars missions in the 1990s. Instead, we had a 30-year gap. A generation of engineers who never built large engines. A knowledge extinction event. The astronauts who never flew. The missions never launched. The future we could have had, traded for short-term budget savings and bureaucratic inertia. We didn't lose to Russia. We beat ourselves. But the story doesn't end in failure. There's a resurrection underway, though it took 3 decades. SpaceX developed the Raptor engine, full-flow staged combustion, even more thermodynamically advanced than the RD-170. 500,000 pounds of thrust per engine and climbing with each iteration. Elon Musk studied the RD-170 closely. He learned from Soviet engineering and from their willingness to pursue difficult solutions. Blue Origin developed the BE-4, American-built oxygen-rich staged combustion, designed to replace the RD-180 on the Vulcan rocket. The first BE-4 flew in 2023. It took 30 years, but America is finally rebuilding the knowledge we lost. But here's the lesson we must not forget. The F-1 wasn't killed by budget cuts. It was killed by assumption. We assumed the knowledge would always be there. We assumed we could rebuild whenever we wanted. We assumed documentation was enough. We assumed wrong. 3 F-1 engines sit in museums: the Smithsonian, the Kennedy Space Center, the Johnson Space Center. Visitors walk past them, take photos, and marvel at their size. But these aren't monuments to triumph. They're monuments to forgetting. The RD-170 still flies, because Russia never assumed they could afford to forget. They kept the engineers employed. They kept the production lines open. They preserved the knowledge, even when they could barely afford to eat. We went to the moon with engines we can't rebuild. We launched satellites with engines we had to buy from our enemies. The question isn't whether we can recover. We are recovering. SpaceX and Blue Origin prove that. The question is whether we'll remember this lesson or repeat it, whether the next generation of engineers will preserve what they build or assume it can always be recreated later, whether we'll value institutional knowledge or treat it as disposable. The F-1 proved what America could build: intensity medium. The RD-180 proved what America forgot. And somewhere in a museum, the most reliable rocket engine ever made is gathering dust because no one alive remembers how it worked. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.